Hi, I'm Suhail Sherif, and I'm going to be talking about lifting to parity decision trees. This is joint work with Arkadev, Nikhil, and Swagato. And I'll be starting with an overview of decision trees and parity decision trees, giving an example of how they're relevant to proof complexity and why we care about parity decision tree lower bounds. Then we'll move on to our theorem, which is a lifting theorem from decision trees to parity decision trees. And we'll pretty much see the whole proof of it, and then we'll go to what our notion of a stifled function is. Most of us have come across decision trees before in computer science. It's a very natural model of computation. It's very simple and also very useful. You have an input, which in our case here is an n-bit string. And we're going to run down this tree from the root to a leaf in the following manner. We start at the root, we query whatever bit is specified at that node. And depending on what the value of the bit is, 0 or 1, we take that corresponding edge out of that node. And we continue this until we reach a leaf. When we reach a leaf, we output the label at that leaf. And we say that a decision tree computes a relation if for every single input, the output of the decision tree on that input is a valid output. Parity decision trees are very similar, but they're not studied as much and they're not as well understood. The only difference is that instead of having bits to query at each node, we have a subset of bits. And when we query the parity of a subset of bits, we get a single bit, 0 or 1, telling us whether there was an even number of ones or an odd number of ones in that subset of bits. And we do the same thing. We reach a leaf and we output the label at that leaf. Now we'll jump into proof complexity and why these are relevant to proof complexity. And to do this, we look at the following task. So we're given an unsat CNF. That's an unsatisfiable set of clauses. And given such an unsat CNF, we have a task defined, which takes as input an assignment to the variables of the CNF. And it outputs, what we're supposed to output on that input is any of the clauses that are falsified by that assignment. And such a clause is guaranteed to exist because the CNF is not satisfiable. Now, a decision tree or a parity decision tree that actually solves this task is actually a proof that our CNF was unsatisfiable. Even though the correctness of this decision tree relies on it being correct on all 2 to the n inputs, we can actually verify that the decision tree or parity decision tree is correct in just the size of the tree. So if we have a small size decision tree or parity decision tree, that is a short proof that the CNF is unsatisfiable. Now, given that we believe that unsat is not an NP, or assuming that we believe that unsat is not an NP, we should also believe, and it would also imply, that there are unsatisfiable CNFs for which we do not have any small decision tree or parity decision tree that solves this task. And indeed, that is true. It's well known that there are unsatisfiable CNFs that require exponentially large decision trees and also parity decision trees, although that was proven much more recently. So the next step for us is to look at decision DAGs instead of decision trees. So these are ways in which you can compress a decision tree to get rid of redundancy, and it can, in some cases, lead to a huge saving in size. So for decision DAGs, again, we know that there are some CNFs that require exponentially large decision DAGs, but a huge open problem, one of the frontiers of proof complexity right now, is that we don't know of any unsatisfiable CNF that's known to require super polynomially large parity decision DAGs. So for all we know, NP could be equal to co-NP just because of parity decision DAGs. And this is our motivation for studying such parity query models. Now, in this talk, we're not actually going to look at parity decision DAGs. We're going to stick to parity decision trees. And what we're going to do is we're going to show a different way of proving lower bounds on parity decision trees. So the previous proofs here by ITCS and Sokolov are very specific to the problems that they were looking at, and we're going to show a more general way of showing parity decision tree lower bounds. And hopefully that can generalize in time to parity decision DAGs. So what's the problem with lower bounds? How do we prove lower bounds on such tree models? These can be characterized by what's called the adversary method. So what an adversary does is the adversary answers the queries made by the decision tree in order to delay the decision tree from being able to give an output. And this characterizes decision tree complexity in the sense that decision tree complexity of a search problem is C if and only if an adversary can force the querier to make C queries. And this can be easy to reason about just by looking at which bits are queried and which bits are unqueried. Then we can think about what we should answer to a new query in order to make the least amount of progress for the querier. But in the case of parity decision trees, we're not fixing bits. There are no queried and unqueried bits. Instead, there are parities that are queried. And this can be very hard to reason about. And I believe it's the main reason why we don't have as many parity decision tree lower bounds. So we did what people generally do in such a situation. What we proved is a lifting theorem, that for any relation S, the parity decision tree size of S composed with the 3-bit majority function is at least the decision tree size of S. And it follows from this that we can find unsat CNFs, which require large parity decision tree size. And all that we need to do in order to find such CNFs is to just prove a decision tree size lower bound, which is much easier. We should note that this holds for many other gadgets, not just for the majority gadget on 3 bits. It holds for indexing as well. And Paul Beam and Sajjan Korath independently proved a similar theorem, and which is also being presented at ITCS. Their theorem focused just on the indexing gadget, but that's because their paper was more generally about properties of composition with the indexing gadget. Right. So what is this composition with majority? Why is composition helpful in lifting theorems? For that, let's just see what a composite relation is. So say you have a relation that takes in as input a 5 bits. This relation composed with the 3-bit majority would take in as input 15 bits, which is divided into 5 blocks of 3 bits each. So each of these blocks I'm going to call a gadget. And given these 15 bits, by applying the majority function on each block, we get an implicit 5-bit input to the original relation. And any valid output on our implicit X is a valid output for our composed relation. And the reason composed relations are so useful is that these gadgets kind of act as shields that shield you from the implicit input. So although we're making parity queries to the Y variables, in some sense, that's restricting the ways in which we can affect the implicit X. And what we will prove is that it's going to be equivalent to just querying X instead of making parity queries to X. And this is how a general standard lifting theorem lower bounds go. What they eventually come up with is an adversary that answers the more complicated queries, which in our case are parity queries. And internally, this adversary is going to use a decision tree adversary for the original relation. And this allows us to show that the number of queries needed for the parity decision tree is going to be at least the number of queries needed for the decision tree on the original relation. And with a slight modification of this outline, we could even show this for parity decision tree size. We should note here that lots of lifting theorems have been proven in the past, but none of them imply this specific statement. There are some that do show lower bounds on parity decision tree size, but the lower bound that they show are just 2 to the power randomized decision tree complexity of S, which is weaker than what we want. So what property do we use of parity queries and how do we work against them? It's really quite simple. So suppose we have some parity constraints. Let's see how the set of solutions changes depending on what those constraints are. So initially, when there are no parity constraints, all your bits are free, which I'm going to represent here as these empty boxes, which just can be filled independently with whatever bits we want. Now, suppose someone adds a constraint here, x2 plus x3 plus x6 is equal to 1. We're going to view this constraint as a constraint on x2. It's just saying x2 is equal to x3 plus x6 plus 1. And all the bits other than x2 are completely free. And we're going to represent this by just putting a d where x2 should be, saying that it's dependent on the others, but the other bits are entirely free. And as we get new constraints, each new independent constraint adds a new dependent bit, and all other bits continue to be free. And to make this formal, this is just Gaussian elimination at play. These are just some bits that are pivots. the rest of the bits can be set completely freely. And using this, we're ready to actually show an adversary against a PDT. So what we need to do is, for every parity query that comes our way, we should tell, as an adversary, we should be able to give an answer that delays the parity decision tree from giving an output. So the parity queries are going to be made to these 15 bits at the bottom, which are an input to our composed relation. And the 15 bits at the bottom are going to implicitly define an X. Since we don't know any of the bits at the bottom, we don't know what the implicit X is. Each bit could be 0 or 1 independently. And say we get our first query here, which is just what is the parity of these 3 bits. What we're going to do is we're going to just answer this query arbitrarily, and we'll choose one of these bits to be a dependent bit and the others to be free. So in this case, we choose the bit in the second gadget to be dependent, and all the other gadgets still are completely free to choose their bits. Now, given that there's a dependency in the second gadget, what we will have to deal with it eventually, and that's what makes parity queries annoying. But the fact that we've composed with majority actually allows us to ignore that dependent bit completely. And to ignore it, we have to ensure that that bit is irrelevant. So what we're going to do is we're going to actually fix the second gadget completely. We're going to choose a value of our second bit. So we're going to query what is the value of the second bit of the implicit X. So for this, we're using our internal adversary against the relation S. And say our adversary tells us that the second bit is equal to 1. Then we're going to fill in the rest of the bits in the second gadget to 1. So now the second gadget is always going to output 1. It doesn't matter what the dependent bit is, and all the other bits are free. This is a very good state of affairs. And we can continue this process. The parity decision tree makes more queries. There are more dependent bits that are created. And we've made more queries to our internal adversary to find out what those gadgets should output. And at some point, the parity decision tree reaches a leaf, and it's going to output some value O. Now, notice that in this example here, the first and fourth gadgets are completely untouched. The parity decision tree does not care about what inputs there are over there. It's already confident that the output is O. So that means that it doesn't matter what the values of the implicit X are in the first and fourth bit. We already know that that O is a valid output for the implicit X. And if we can actually give an answer to what is the value of S on the implicit X, that means that the decision tree adversary has already forced us to make dt of S many queries. That implies that the number of dependent bits over here is already dt of S. And so this actually gives us a parity decision tree lorem, saying that the parity decision tree has made at least dt of S many queries. So this is a lifting theorem already. It's not a size lifting theorem, but it is a query lifting theorem. And we can adapt this to make it a size lifting theorem with just one small change. And that is, earlier we said that the adversary can just answer arbitrarily whenever a dependency giving query was made. Now we're going to change that and say that the adversary answers in such a way that we go to the smaller subtree of the PDT. So now we're guaranteed that the number of dependencies that come up is at most log of the PDT size. But on the other hand, we know that the number of dependencies has to be at least the decision tree complexity of S. Putting both of these together, we get that the PDT size has to be at least 2 to the power decision tree complexity of S. Now, what about other gadgets apart from majority? Let's take majority on 5 bits as an illustrative example. In such a case, we can ignore 2 dependencies in each gadget. Even if 2 bits are dependent, we can completely ignore them if we fix the other 3 bits to be the same. So the number of dependencies that are going to arise is going to be twice the decision tree complexity of S. And so if we go through the same calculation, we see that the PDT size of S composed with the 5-bit majority is at least the decision tree size of S squared. And what we're using here is the fact that these gadgets allow us to just ignore bits. We are allowed to ignore some number of bits while still being able to set the gadget to 0 or to 1 as we wish. And this is what we're calling a K-stifled gadget. So a gadget G is K-stifled if for any subset of K bits, we can completely stifle those K bits by just not looking at them and setting the rest of the values and fixing it to 0 or fixing it to 1 as we wish. So in such cases, we have the lifting theorem that the parity decision tree size of S composed with G is at least the decision tree size of S to the power K. Some examples of stifled functions are, as we saw, majority. So majority on 2K plus 1 bits is K stifled. The indexing function on K plus 2 to the K bits is K stifled. And the inner product function is 1 stifled. It is not 2 stifled, no matter how large it is. And this is a bit surprising because we expect F composed with inner product to be, or so in this case, parity decision tree size of S composed with inner product to be at least the decision tree size of S to the power n, where the inner product is on n plus n bits. But we're not able to prove that with this method of stifling. So that's an interesting open question. What other properties of PDTs can we use? How can we prove a lifting theorem in order to show that the PDT size scales as the size of the inner product gadget increases? Hopefully this will be insightful and give us more tools to work against PDTs. The obvious open question is, how can we make the simulation theorem also work for DAGs? Simulation theorem is just the same as lifting theorem in this slide. And yeah, these are the main 2 open questions. Thank you for watching.